Good afternoon, everyone. It's Thursday. It's just after 2 o'clock, and welcome to the M Word. My name is Robin. I'm the Technical Director of Man and Machine in the UK, and welcome to our new studio for the second week in a row. I've moved things around today because I wasn't quite happy with where things were last week. So what's really frustrating, you can't see it, but I can't see my preview screen because I've decided to put a big light in the way. So if you see me ducking or jumping or turn around the corner, Lord. There we go. We can just about see where my preview is, but it's all good. So thank you very much for joining us today. As I say, welcome to the M Word. And for those of you that are new, the idea behind these sessions is to really share a bit of a tea break or a coffee break in the afternoon, and talk through some tips, some tricks, industry workflows, best practices, or just a little bit of training really on some of the different Autodesk technologies that we sell and support here at Man and Machine. So over the weeks we've done some InfraWorks, we've done Revit, we've done Inventor, we've done Enscape, we've done AutoCAD, 3ds Max, the lot. And it's got to the point where it gets quite difficult to try and figure out what topic to cover week on week. So we've tried something new, and yesterday we put a poll up on our LinkedIn page. So do give us a follow on LinkedIn and check out what we've got on there. And we decided to ask you out of a few different options which you would like to see. The last time I checked, about 5 minutes ago, because we had a little bit of a mare with the Wi-Fi just before going live when it decided to go down. But last time I checked, it was a tie between Revit no, we did that last week. Revit Railings, which would be a nice follow-on from last week, or Autodesk Inventor FEA, Finite Element Analysis, so simulation. I'm just looking over at Ellie to see if she can tell me it's still a draw, which it is. So it's a draw. I'm going to get a coin out. I'm going to toss a coin. I'm not going to choose manufacturing or Revit because I think we all know who would win. But if I flick this coin, heads for manufacturing, tails for, I'm going to do that again because I saw what it landed on. Heads for manufacturing, no, tails for AC. Come on. Yeah, it's heads. Sorry, it's heads. I won't celebrate. So we're going to do Inventor. And that works quite well because I think we did Revit last week. So I like to do on and off between manufacturing and construction. But maybe that gives us our topic for next week. Maybe we do Revit Railings next week instead of this week. So we'll do some FEA for 25 minutes or so inside of Inventor. Using the default out-the-box tools. We won't go into Nastran today, although maybe if that's something that you'll be interested to see at a later session, please let us know. We'll focus on the core FEA tools inside of Inventor. So just give us a like and give us a subscribe if you like what you see here today. And don't forget to check out our YouTube channel. We've got a whole raft of other videos and content down through there. So please check it out. Give us a feedback on what you'd like to see more of. And some of those videos get quite specific. They're a lot more in depth. So you have like an hour and 15 demonstration on Revit, 45-minute deep dives into Inventor, looking at Fusion and generative design. And not just from myself, from a load of other people in my team here at Man & Machine, who are a lot more intelligent and handsome than I am. But yeah, go and check them out and let us know what else you would like to see. I'm going to stop going on now and show you some content. So let's make myself go small into the corner. There we go. And let's share my screen. I haven't got anything open yet because I didn't know whether we was doing Inventor or Revit. So we're going to open up Inventor. And I'm using 2023. Typically, you'll know by now, I always tend to use the latest Autodesk software. So we're using 2023 today. This functionality that I show, again, it's probably not changed. Certainly for the last 5, 6, 7 years, there's nothing that I'm going to be showing today that's going to be any different to what's in those older versions of Inventor. So just bear that in mind if you're not quite installed on the latest version yet. So I'm going to try, if time allows, to maybe do 2 examples. Maybe we'll throw together a quick part and do a quick part analysis, and then maybe we'll do a quick assembly analysis as well. And then we'll see how time goes. We might be able to get in some frequency analysis for vibration, and perhaps we might be able to get some parametric study in there as well. So without further ado, I'm going to start a new part. So we'll start off within a basic part inside of Inventor. I forgot to thank all of you that voted. Thank you for those of you that voted on the channel for this content today. So let's start with a part. And we want to do something fairly straightforward because I'm going to model it up from scratch so that hopefully the idea is you can follow along in your own time. And let's go ahead and create something. What should we create? A basic bracket or something like that. So let's go ahead and create a 2D sketch. Let's go ahead and use the front plane to draw this sketch on, and we're going to use a center point rectangle, 2-point center. I'm just going to do it vertically. Oh no, I've not used Inventor yet on this new machine. I'm going to have to change that because it's going to frustrate me. Let's get it into metrics. Sorry for all of those watching using Imperial. File, configure default templates, millimeters and ISO, please. Yes, of course I want to overwrite. Thank you. Try that again. And let's create a new sketch. 2-point center rectangle, and let's draw that in. I don't want to do anything too thin here, and I'll explain why in a second. So I'm going to draw a fairly chunky bracket for the purpose of this. So maybe let's go, I don't know, about 150 wide, and let's go for something that is a little bit longer. So we're going to say that times by 5. So there's my piece of material. Maybe we're going to cut a few holes out of this, which we'll do in a second. So let's just start by finishing that off. Let's extrude it in both directions, and we'll extrude it by 50 mil, like so. And then maybe, yes, I know I could have done this as part of the same sketch, but I'm not going to because I couldn't be bothered. Let's go ahead and pick up a slot, center point slot. So let's go from there out to the side. I'm just going to do this by eye. About 30 mil will do for the purpose of that. Perfect. Let's finish and let's extrude that through as a cut. And we're just going to rectangular pattern that one in both directions. We're going to go by a spacing. Yeah, that's fine. Let's go for 100 mil. No, that won't work, will it? How big do I make it? Yes, of course it will. 250. Maybe less. 200. There we go. And I want to go in the other direction as well. Flip. And we're going to go and do 200 again. Perfect. So there's our component. Nice and simple. Once we have our component, whatever it looks like, it's important we give it a material. So the way in which the Inventor FEA works is it uses the physical material from the part. So within the Inventor material browser, physical materials, this is not the appearances, which are just to do with the paint, the finish, the color. The physical materials all have physical properties against them. So if I come down and say, let's make it something soft, let's make this aluminium. If we come and select this particular material here and right click it and go to its properties by editing it, you can see it's got physical materials. And in here we've got some basic information about its thermal loads and strengths, but also its mechanical data and its general strength as well. So we've got our tensile strengths, our yield strengths, the behavior of the material, and so on and so forth. This is what it's going to use when we're working in that FEA environment. So if you've got your own materials that you want to make or that you want to use, just make sure that those mechanical properties and strength properties are filled out. And then we can go ahead and assign that aluminium material to our component. No, I don't want resin, I want aluminium. Good. And there we have it. So I'm just going to do a quick save. I'm just going to throw this down on my desktop just so I've got it there. Let's just call it FEA part. And with this component, we're going to say environments, and we're going to take this into the stress analysis environment. So take it into stress analysis. From here, we create a study. We've got a couple of different study types that we can do in Inventor. We can do static analysis, we can do modal analysis, or we can do shape generator. Shape generator, I think we'll talk about on another session. We've got a good YouTube video on our channel, so check that out, although it's a little bit dated, probably needs an update. But generally speaking, static analysis will allow me to put some load onto this product in a static way, so that component is grounded. We put some load on it or on a part of that component, and it will deform as necessary. Modal analysis will vibrate the product, so it's looking at frequencies. Shape generator will generate a shape based on a given load or based on a given predefined fixed shapes. So we're going to work on static analysis here. We've got some contacts. I won't use these from a part perspective because they don't really matter. Okay, so we click OK. And then from here, what we're going to do for the purpose of this is we're going to imagine that this thing is basically bolted to the wall using these holes. So we've got 3 bolts on the wall, and we're going to stick a big old load on the top, and we're just going to see how the thing moves. Not much is the honest answer based on what we've drawn here, but again, you'll get the example and then we'll take it into an assembly. So with this, we've got our component set up. We can set up a parametric table. I don't think we'll have time within the half-an-hour session today to go through that, but what parametric table allows you to do is run several analyses at the same time. So we can say, I want to analyze this based on a length of X, Y, and Z, or a thickness based on X, Y, and Z, and it will give you all of the results and specify which ones meet a safety factor and which ones don't meet a safety factor, which gives you a really beneficial way of modeling and getting results based on your requirements. But for this, we're just doing one design. I've already assigned a material. I can override that material should I want to, so I can, in the FEA environment, test some different materials to look at the results. We can work on thin bodies. I don't have anything that's classified as thin within this particular example, but if you've got some sheet metal components, for example, inside of your designs, we need to work with them using surface geometry. So if anything is particularly thin, like a piece of sheet metal or a piece of thin material, Inventor will create shell components. So it will create an offset face and use that for the simulation, because the thickness of the component won't allow it to give you a realistic result. In this case, we're not working on any thin parts, but if you were, you would find them and it would detect them and work through them for you. We need to set up our constraints. So for this, I'm just going to say that I've got this component fixed, and I can fix it either on the back face, and imagine that's glued or welded, let's say, to the wall, or I can say that it's connected around a given edge or a given part of that component, like a point. I'm going to be lazy once again and just say it's the back face here that's stuck, and I can press OK. And that will imagine that that back face is stuck on the wall and it won't move. So it's physically glued in place, if you like. We then place our force. So we can place our force again on any face, on any edge, or on any point. Okay. And when we're defining our face force, we put it in newtons. So again, this isn't going to move that much. But if we imagine that this is bolted in and it's holding something on the top, we're going to click on the top here. We're going to throw a load of newtons on it. I'm just going to go mad and put 500 newtons on there. And what that will do is it will put this big yellow arrow in its place. We can control more specific inputs with regards to an XYZ permission, location and force directions. And we can also change the display of this glyph. We can change the color, make it bigger, make it smaller, depending on how big your part or assembly is or how small it is. We can control that to make it look as we need it to look. We can also add pressures. We can add bearing movements, moments, so twists or rotations. And we can also add gravity as well as remote forces or body loads. I'm going to put gravity on at the same time. I'm going to specify gravity as being down and leave the default settings for gravity on. We don't need to use contact because this is a single component. If we had several components in here, we'd need to choose how Inventor works with those components against each other. So are they bonded and welded together? Do they slide but not separate? And we'll try and cover that in a second in a assembly example. To create a simulation, we have to create a mesh. The mesh will basically triangulate this component and turn it into a mesh. So we get all of these triangles, and the simulation is carried out on the triangles rather than the entire solid lump. It works with each of the triangles individually and sees how they react with one another, and therefore gives you a much more accurate and a much quicker representation than if you are trying to do the whole thing on a solid lump. The thing to bear in mind is the size of that mesh. Now this is a pretty generic, rubbishy example if I'm completely honest. So the actual triangle size isn't going to matter that much, but the triangles you see here are representative. They're not actually true to the shape of the actual mesh. That said, the more refined your mesh, the better results you're going to get. So if you were particularly keen on looking at the displacement of these curvature faces, you would want to do some refinements, which we will do in just a second. I'm just going to go ahead and hit simulate and press run. This is going to be very quick, and what we'll get is an instant bit of feedback on our simulation. Now don't panic, because what we're looking at is an adjusted result. Okay? When we get our results in Inventor, we have the ability to view them underformed. We have the ability to show them actual, so actually what is deforming, all the way to 5 times adjusted mess. Looks a bit like jelly. So we can go in and get an idea of A, how the thing is actually moving, as well as B, the directions in which it's moving, to get an appreciation of what that actually looks like, whether that's adjusted 5 times, 0.5 times, or somewhere in between. The truth of it is, this is moving very little, so the von Mises stress is like 0.03 at its maximum point. The safety factor never dips below 15. By the looks of this, it's all blue, and we don't get any minimum or maximums. If we look at the displacement, the maximum displacement is so small, we can't even get a proper number for it. So we have a tiny amount of displacement, as you would expect with the kind of result that we've got. Let's change it and show you how easy it is to change this simulation. Let's leave that on adjusted 1 times. We come back in, we can use our browser, we can go to our loads or our constraints, and we can change them. So I'm going to change and delete my force and reapply it. And this time I'm going to place the force specifically inside these 3 spherical faces. I'm again going to put on 500 newtons on there just because I can. And with that, I'm also going to refine the mesh. I can add local mesh control to those spherical faces and choose how big I want the element size to be for those specific faces before telling it to go ahead and update my mesh. The more refined you have your mesh, the longer it will take to compute the results. And again, the visual feedback that you're getting from Inventor is only representative of the actual mesh that you're going to end up getting. Okay? So don't think that the triangles there are the actual mesh, they're just a representative shape. This is where I find out that I've probably gone too small and this is going to take far too long to compute the mesh, but we're going to give it a couple of seconds and let it compute away. What we'll end up with is an area around those filleted faces or those spherical faces that you'll visibly be able to see is much smaller. So there are many more triangles. Because there are more triangles and the triangles are smaller, each section of result within those triangles is going to be of greater accuracy. So the more refined your mesh, the better accuracy you have to the actual shape. Therefore, the better results you have. If you for example, compare the shape on the mesh, ignore the green edge, look at the shape of the mesh. It's faceted. If we go ahead and look at the bottom and look at the shape of the mesh, it's far more refined. Your simulation will take a much longer time to run, naturally. But with those loads on there, we can go ahead and press simulate, go ahead and press run. It should still be fairly quick. It's not really doing anything complicated from this perspective, but it's doing it on a much finer mesh on those spherical faces. So you're going to get more results, especially as those results are where I actually put the load. So we'll give it a couple of seconds, let it compute and show you what it's doing. What we're going to do after that is maybe we'll do a quick modal analysis to show you vibration because it is very fast, and then we'll drop out and do a quick assembly, maybe showing you something more realistic. So let's look at the actual deformation of this part. It's still very, very small. It's displacement of, still a tiny number. The safety factor is still massive, and as you'd expect, it's not really moving. But you can see how within that area, if we look at the adjusted results, we start getting some far smoother and far clearer results when we're figuring out what's stressing and by how much. You can turn the mesh on or off to actually see the parts or the components themselves. We can animate the actual deformation. So if we hit animate and press play, it's going to go ahead and animate the stress happening, and we can export that out to video format should we want to, and increase the steps to make it smoother. We can probe any area to get information from that particular area in turn. So I can click any point and get some feedback on the stresses or whatever result you're looking at. We can plot that in convergence. We can look at color bars. We can change the shading of that particular result. And generally, it's all very self-explanatory. It's quite quick, it's very user-friendly, and it sits directly inside of Inventor. Let's go ahead and create a new study. This time, not that you would with an example like this, let's go ahead and do a modal analysis. Let's put it through, 17 numbers of modes. The frequency, we'll just go number of modes, 17 different modes. Hit OK. Again, you assign the materials, parametric body if you want to, thin body analysis if you want to, and then we add our constraints. So this time I'm going to add a fixed constraint on this side. We can come in and add additional forces, so on and so forth if we want to. Go ahead and hit the mesh view. Go ahead and hit simulate. And what this will do is it will essentially stick this on a vibrating plate and allow us to see what happens with regards to the different frequencies. As you can see, we can go through the frequencies and see the results. Again, either actual, underformed, or adjusted X amount of times. Looks like a shark. So what we can do is see that we start getting results based on that, on a frequency analysis and those different frequencies. I've just said go ahead and do 17 different frequencies, but it might be that you want to do some very specific ones, in which case you would just say, I want to do frequencies from X through to Y. Straightforward and fairly simple. Let's just close that down and whiz through a very, very quick example using an assembly. So let's create a new standard IAM. And with that IAM, we're going to go ahead and create some simple parts. So let's create a part. Let's do a quick shelf. So let's just say that we want to have a bracket. Let's press OK. I'm going to place it over here. We're going to model it up from scratch. So let's look at this from the front. We're going to do this fairly simply just because we're a little bit pushed for time. So let's say that we've got something that looks like this. We're going to have 25 mil upwards. 25 mil, that's tiny. We're going to say that we've got something that is 250 mil that way, 250 mil that way, and triangular. Okay, finish that, extrude it in both directions by about 80 millimeters. Maybe I'll put a fillet on just to make it look a little bit nicer and give the simulation something to think about, like so. And let's go ahead and make that something metal. Again, I'm going to use aluminium just because it's there and it's easy. And then we're going to return. We're going to have another bracket in there as well. And then we're going to create a shelf. I'm not going to bother with any actual fixings in here. I'm just going to kind of draw the thing. And then I'll use the functions inside of FEA to connect them together alongside my joints. So let's say that I want my shelf to be 350 in depth and I want it to be 980 in width. I'll use the same thickness, which was 18 millimeters. So let's place that 18 mil. And then again, I'm going to use the same material just because, and we will return. We don't want you grounded. Let's unground you. And let's, with this all floating around, let's just get this constrained quite nicely. So let's constrain. Let's go ahead and grab the origin point of the assembly and grab the YZ with the YZ. Apply the XZ with the XZ. Apply. And then we'll have a flush XY and XY. Apply. We're then going to say constrain face to face, like so. We'll have a flush face to face with an offset of maybe 100 mil. Apply. And then we want to have the back so that it is flush face to face. Over here, let's have these two flushed. Let's have this one and this one 100 mil apart. So I'm just mimicking it. I could have put symmetry on there, but I cannot be bothered to do that for this example. It's just as quick to do it without. And who needs symmetry for this example? Hit cancel, and we have our shelf. What we're going to do with that is just do a quick save just to make sure it doesn't drop its lunch. And we're going to go straight into the FEA environment. Now, when you're working with an assembly, you need to work with constraints. Constraints will figure out how the components contacts, how the components are connected together. So we're going to create a study, and with that study, again, I'm going to do a static analysis. But down the bottom, you've got contacts. So we're telling Inventor, whenever you find a component within a given tolerance, in this case 0.1 of a millimeter, so anything within 0.1 millimeter, imagine that that's bonded or glued or welded together. We can change that, and we've got different types of contact. I'll talk through them in a second, but imagine that they're bonded together. They physically can't move apart, Okay? In other words, they can only force each other to displace. We hit OK. And what you can see here is same things. We assign parametric table if we want to, assign materials if we want to, find thin bodies if we need to. Let's add our constraints. Really simple. We have a fixed constraint to the wall on this and on this. Okay, those two are fixed. We then have a force. We have a force on top of here, which is 1,000 newtons. Okay. We have gravity, pulling this down as well. Define the location for gravity if you want to. I'm going to change the glyph to some other color, like blue, and make it smaller. And then I'm going to talk about contacts. We can do automatic contacts, which is what Inventor does by default, or we can do manual contacts. If we tell it to do automatic contacts, we then can't do manual. If we tell it to do manual, we then can't do automatic. Okay? As you would expect with an example like this, everything bonds because it's within that tolerance. The different types of constraint or contact I have are bonded. Again, they can't move apart. Separation, you're telling the components that whilst they might be touching now, they are allowed to separate. A sliding without separation, they can't separate, but they can slide. Shrink fit sliding and shrink fit non-sliding, it's the same, but it's difficult to explain. So when you've got a shrink fit sliding or a shrink fit non-sliding, I'll come back to that one. The slightly different way of explaining it. Give me a second and I'll give you an example. And then act like a spring. In this case, everything's bonded, and I don't physically want things to. You don't physically want things to separate, because in reality these wouldn't. They'd either be glued or screwed, or if it's metal, maybe they're welded together as well. So what we're going to do is go ahead and add our mesh. I'm just going to stick with the default mesh here just for the purpose of time. Again, just take those triangles with a pinch of salt. Those triangles are there just to represent. They're not necessarily going to give you everything. And then we're just going to hit simulate and run. It's going to take a little bit longer than a single part because I've got multiple components in there. But what we're going to do is see that those components are now reacting with one another. Okay, so that shrink fit non-sliding, by the way, imagine that you've got like an O-ring or a ring that's sitting inside a cavity. That is within another component. So it shrink fit is that's within that frame or that seat, if you like. It can slide, so it might be able to spin around within that compartment or in that pocket, but it can't separate, or it's stuck. It's in there, but it physically can't move. So if you've got an O-ring or something like that, that's what you would use for the shrink fit. So from here, same results: underformed, adjusted, and adjusted. You can get an idea of exactly what results you're going to get. You can animate them, you can probe them, and exactly the same functions as we saw within the single part. The main difference is we've got 3 parts. Okay, so at any point we can come in here and right-click these components and turn them off to see the individual stresses. Oops, undo. To see the individual stresses of. Now I've done it. Visibility. To see the individual stresses of the individual components. So we can actually look at the bracketry component on its own and start looking at what's going on the top face, which is bearing a lot of the load as that's pushing down on it. We can go and have a look at the underside in that and see how it's turning. So you're still an Inventor part. You've still got all of the same functionality that you've got inside of Inventor to be able to hide, turn things on or off, and interrogate that in any way you see fit. And again, because you're in that component, we can come back at any time out of the analysis environment. We can come into any one of those components and we can make a change. So I can come within this component here. I can make that extrusion tiny, tiny thin at 2 millimeters. I can then go back into the simulation environment. I can tell it to find thin bodies, convert those to surfaces, recreate the mesh, and then simulate. I need to regenerate the force, my mistakes. We had it on 1,000, didn't we? 1,000 newtons. Apply. And the gravity we had on there as well. The reason I'm having to redo those again is because I now don't have that solid there. It's a thin body. And again, that's purely there to invalid load force 1. Why? Oh, I added a new one and didn't update the existing one. Practice what you preach. Simulate, go. So thin bodies need to have a surface for the reason that you don't want any self-intersection appearing and things like that. So it will treat them as a thin body and surface them instead. We can then start looking at those results based on those mid-surfaces and getting the information out of Inventor as you see fit. And really, I've got a little bit over the half an hour there, but that's kind of what I wanted to show today. Looking at, or I say that's what I wanted to show. It was a 50-50 on the result that we did on the poll. We flipped a coin. We showed Inventor FEA. Great. So that is what I wanted to show with regards to FEA. I think what we'll do next week, unless we get an influx of people wanting to see something different, we will use the other example that you guys wanted to see this week, which missed out on the toss. So we'll do Revit Railings next week and show you how you can make your own configurations of railings inside of Inventor. So I do hope that's been useful. Sorry for waffling on a little bit today. It feels like I've waffled on a lot, but hey, what can I do? So hope that's been useful. Again, check out our other channel videos. Give us a like, give us a subscribe, give us some feedback, and we'll see you all at the same time, 2 o'clock next Thursday. Until then, take care, enjoy the rest of the week and your weekend, and I'll see you soon.